There we go. So basically from here, so now again, we can see that the dependence of the potential now matters. Because again, if this thing is less singular than 1 over r squared, so if this thing went like a Coulombic potential 1 over r, this term here is going to become subdominant as r goes to 0, right? So as r goes to 0, this term here is going to go to 0. This term is also going to go to 0, which leaves only the constant term. But if this thing was 1 over r squared dependent, the r squares would cancel, which means that this thing would have a constant dependence, which is, you know, plus or minus okay. This term is still going to go to 0. But if this thing was any more singular than 1 over r squared, again, this thing is going to blow up and go to infinity, which then would give us, again, that singular term. So we won't be able to use this, again, polynomial type solution here. So let's look at the limits and what this thing is going to do as r goes to 0. So again, as r goes to 0, this term and this term are going to simply go to 0, which means that we're going to be left with then minus h bar squared divided by 2 mu times s minus 1 plus L times L plus 1 h bar squared divided by 2 mu must all be equal to 0. Good. H bar squared is a constant, so we can divide those out. The 2 mu's are also constants, so we can divide those guys out as well. So finally, what we're left with then is that s times s minus 1 minus then L times L plus 1 must all be equal to 0. So here we want to put restrictions on the s's based off of the l's. So let's write this then as s squared minus s minus L, I'll leave it this way, times L plus 1 is equal to 0. This now gives us a quadratic, which we have to solve for s. So we can then say s then is equal to minus b, which is 1, plus or minus the square root of b squared, so that's 1, minus 4 times a, which is also 1, times c, which is a negative of this stuff, so that becomes a positive, L times L plus 1, all divided by 2, right? Let's square and multiply all this stuff out. So this is going to become 1 plus or minus the square root of, so 1 plus 4 times L squared plus 4 times L, right? All divided by 2. But 4L squared plus 4L plus 1 is the same thing as 2L plus 1 quantity squared. So this is the same thing then as 1 plus or minus the square root of 2L plus 1 quantity squared divided by 2. So it's going to be equal to 1 plus or minus 2L plus 1 quantities, or divided by 2, right? Almost said quantity squared. Great. So if I add these together, so what happened is this is going to become a 2 here. So this is going to be the same thing as what? L plus 1. Right, under the plus term. And then under the negative term, if I subtract these guys, the ones are going to cancel, so this is going to be simply negative L. So these are then my possible S values that I'm allowed to have. So basically what this says then is based off the structure of our differential equation, as then R goes to 0, we're only allowed to have solutions then that U is equal to either what, R to the L plus 1 or R to the negative L. Well, from here we can automatically see that this one won't work, because if I have R to the negative L, right, that brings us back to the fact that this thing would become more singular, which means that this thing would blow up as R goes to 0, which means that we can't keep this term. So this term has to automatically go. So we can only be left with this term. Good. Now the other thing is, remember that R is equal to U divided by R, which means that R in this case then would be equal to simply R to the Lth power. So good. So what does that mean? Well, that means that basically we wouldn't be able to have the 0, right? So what has to be true then is that L must be greater than 0 in this case. And basically the reason for that is because if L was equal to 0, right? So if this thing went as R, this thing would also go as a constant, which basically means that what? If I took the gradient of something like 1 over R, remember from E and M, sorry, the square of this guy is equal to minus 4 times pi times delta R. Which basically means that if L was equal to 0, then this thing would have to satisfy a delta function, but we don't have a delta function. We have basically a particle sitting there. So basically this solution is not a valid solution since we don't want a delta function. We want something which is less singular than that is. Okay? So basically what this tells us then is that this is the only solution we can have, but what has to be true then is that L must be greater than or equal to 1. Okay, so L has to start off at 1 in this case. Is it okay? Good. So automatically this tells us about L. Now the other thing is, remember from classical mechanics, right? When we talked about something like a gravity well, right? We had the gravitational potential, which basically did something like this. Right? This was the gravitational potential. But then we also had that centrifugal term, which basically did something like this, which meant that the total, get a different color, the total potential then, or the effective potential, basically did something like this, right? So in this case, what we argued in that class, and we're going to argue it again here, is that for this thing to be a bounded structure, right? So if I had, for example, this was the sun and this was the earth around the sun, then what had to be true was that the earth had to have an overall negative energy to make sure that this thing went between two turning points, so that this thing, if this was the sun, then my poor little earth out here had to be bounded by an outer radius and an inner radius. So as this thing was going around the sun, it could wobble back and forth between the two, but to have a stable bounded orbit, this thing had to have an outer radius and a low inner radius, which means that this thing had to have, this is my inner radius, and this is my outer radius, so this thing had to have turning points to it. So for the hydrogen atom, it has to basically be the same thing. So what we have to have is that the proton and electron are bounded, which basically means that, again, our energy must be just like the classical case with gravity, it must be negative. So for bounded solutions, the energy then must be negative. Okay. So here we're just going to write our energy, which was on the right-hand side, then as minus the absolute value of the energy. Everybody's okay? So let's go back to our differential equation. So now we have minus h bar squared divided by 2 mu times the derivative respect to r, plus L times L plus 1 times h bar squared divided by 2 mu r plus our potential, all then acting on U, must then be equal to negative absolute value of the energy times U. Now, from here, it's convenient to define a new variable. So let's define a new variable. That new variable we're going to call rho, which is going to be defined as the square root of 2 times mu times the absolute value of the energy divided by h bar squared times r. Okay. So basically, we're going to change our radial, we're just going to rescale our radial coordinates. So we're going to rescale it by the amount of this amount. So in this case, then, this differential equation then, or our Schrodinger equation, is then going to become the second derivative of u with respect to rho minus, multiplying through by a negative sign, there we go, minus L times L plus 1 divided by rho squared times u plus lambda divided by rho minus 1/4 all times u then is equal to 0, where lambda we're defining as, for our Coulombic potential, ze squared divided by h bar times the square root of mu divided by 2 times the absolute value of the energy. Okay. So this is our definition of lambda. Guys doing okay? So again, all we're doing is we're using a rescaled position variable and then rewriting our Schrodinger equation this way.
You said that z was an integer?
Yes, so z here I'm saying is from the Coulombic potential. So V of r is equal to z times e divided by r. Okay, so that's where that's coming from. So z represents the, make sure I get this right, this is the number of protons of the nucleus. So basically for the hydrogen atom, z is going to be equal to 1.
Okay.
But this is for something other than that. So basically we're kind of doing it more general here, where z is equal to the number of protons. So basically what we're saying is that the charge here for the nucleus is z times e, and then the charge of the electron is also e. So that's why it's an e squared. So this is equal to z e squared over r. So I'm allowing for something other than just a hydrogen atom, basically. Guys doing okay? Not too bad. Good. So basically what we've done so far is, let's go back, we have looked at the behavior of the wave function as r goes to 0. As r goes to 0, we then found the behavior of our wave function as r goes to 0, and we argued that it has to go as u to the L plus 1. Where L in this case has to be 1 or greater. So what we're going to do then is now use this version of our Schrodinger equation. Okay. And now look at the opposite limit, and we're going to take rho here goes to infinity. Okay. And then see what happens when rho goes to infinity. So basically what's going to happen is rho goes to infinity, this term here is going to go to 0. And this term here is also going to go to 0. So here we're going to look at as rho goes to infinity. So in this case, we're going to be left with then what? The second derivative of u with respect to rho minus u divided by 4 equals 0. So this is then going to be the behavior of the wave function as what? Rho goes to infinity, which is equivalent to r going to infinity. So what type of differential equation is this?
Separable? No.
It's what?
Is it separable?
Well, it's not separable because there's only one thing on there.
Oh, that's true.
We already separated that a long time ago.
Oh, excuse me.
No, you're fine. So what I really mean is this thing a harmonic oscillator or is it exponential? Those are basically our two choices. So what do you think? Is this one an oscillatory one or is it an exponential?
Let's see here. Oh, hold on a second, doctor. I'm being summoned from away for a second.
Sure.
Sorry, Professor. My grandmother was fussing at me.
No problem.
Yeah.
Did you tell her you're in class?
I'm trying to, but yeah.
There you go.
So it's exponential, apparently.
It's exponential, that's right. Good. Yeah, it'd be oscillatory if this was a plus sign here. So
That's, yeah, okay. I couldn't remember.
Exponential. Good. So good. So this guy tells us then that's what? Well, the behavior of the wave function then has to be exponential as rho goes to infinity. But from here, we can also see that because our wave function must be normalizable, that we can't have the positive exponential term, right? So basically from here, we have to set that b is equal to 0 to make sure that, well, this thing has to be normalizable, right? So here, so basically what we have then is what? Let's recap. So what this says then is that what? In the limit that rho goes to 0, which is equivalent to r goes to 0, our wave function then has to go as what? R to the L plus 1, which is equivalent to rho to the L plus 1, right? In the limit rho goes to infinity, we then have to have this thing has to be going as a decaying exponential. And as we talked about math methods, and basically what we're going to do is we took the r goes to 0 limit here. We took the r goes to infinity limit here, and we want to do then is communicate these two guys together by using what's called an interpolating function. Interpolating function. There we go. So basically, what this means then is that our total solution for u as a function of rho is going to be equal to, well, this guy pasted together with this guy. So this is going to be rho L plus 1 times e to the negative rho divided by 2 times then some interpolating function f of rho. Okay. So basically, f of rho here is the interpolating function which basically connects these two extreme limits together. So here, this is the, again, rho goes to 0 limit, this is the rho goes to infinity limits, and this is the guy which interpolates between the two, which basically connects these two guys together. So basically, what we have to do now is take this solution, plug this back into this differential equation, and then come up with restrictions on what f can be. So this is the part that we actually did in math methods, if I remember correctly. So I'm going to kind of skip to the end of all of this. But basically, if we do that, what we find then is that f here has to satisfy the following expression, which says that 0 then is equal to the second derivative with respect to rho plus 2L plus 2 divided by rho minus 1 times the first derivative with respect to rho minus 1 over rho times L plus 1 minus lambda, and all this times f. So our interpolating function has to satisfy this particular differential equation. Now from here, what we did in math methods is now we're going to seek a power series solution for f. So from here, we're going to say, well, f then must be some sort of power series solution, which we're going to say is the sum over k of then some coefficient ck times rho to the kth power. Basically from here, again, what we did in math methods is we came up with a recursion relation, which means when we take this solution and plug it back into here, what we finally get is, so again, I'm going to skip some steps because we already did this before. So this is sum k equals 0 to infinity of ck plus 1, k times k plus 1, plus 2L plus 2 times k plus 1 times, or plus ck minus k minus L plus 1 plus a lambda, all times rho to the k minus 1. So in math methods, basically what we argued was that this term here has to be arbitrary. So this must be arbitrary. We can't simply set this guy equal to 0. It has to be true for any value of rho, which basically means then that everything on the interior of the sum then must be equal to 0. And this now gives us our recursion relation. So a recursion relation then says that ck plus 1 divided by ck then must be equal to k plus L plus 1 minus lambda, all divided by stuff. K plus 1 times K plus 2L plus 2.
Oh, wait, Professor, is that a K plus 1 on that exponent or a K minus 1?
This one up here?
No, the row exponent.
Oh, that's a minus. Yeah.
Okay.
Sorry, sometimes my pen likes to bleed a little bit. There you go. Minus 1. There you go. Now, again, what we argue in math methods is that what? If we look at this recursion relation, in the limit that k here goes to infinity, so for very large k values, basically what we find in that case then is that what? The numerator goes as k, the denominator goes as k squared, which means in the limit that k goes off to infinity, ck plus 1 divided by ck goes as 1 over k, which means then that what? Basically, if I sum from 0 all the way out to infinity, what happens in this case then is that what? F is going to go as an exponential term, because remember that exponential e rho is equal to the sum k equals 0 to infinity of ck, but in this case, ck would then be equal to 1 over k factorial times rho to the kth power, which means that this thing would actually go as an exponential. Okay, so now the problem with this again is if we took this solution and we put that into our u solution, so u of rho then would be equal to rho to the L plus 1 times e to the minus rho divided by 2 times e to the rho, which then would be equal to rho to the L plus 1 times e to the rho divided by 2, which again goes to infinity as what? Rho goes to infinity. So as rho goes to infinity, u would also go to infinity, which basically means, again, we're back to the point where this thing is non-renormalizable or non-normalizable. Not renormalizable. Normalizable. There we go. So again, I'm skimming through these because we already saw this in math methods. This will be in the book as well, but since we already went through there, I'm not going to spend too much time on there, but again. So basically, the point of all of this is that we can't sum this all the way out to infinity, because what's going to happen is that's going to lead us to the fact that this thing goes to an exponential, right? So f then is going to end up going to an exponential, which means that this thing is going to be non-normalizable in the limits that rho goes to infinity, which basically means that, again, we're going to have a pointless wave function. So the only way to get around that is to what? What has to be true is we can only sum out to then some maximum amount of k value, where that maximum amount of k value is going to be when this numerator then is going to go to 0. Okay. So basically, what that's going to impose on us then is that we can only sum this thing out to a k max, where ck plus 1 divided by ck must be equal to 0, which is then going to be equal to k max plus L plus 1 minus lambda. Right? Because this thing only goes to 0 either when the denominator goes to infinity or when the numerator goes to 0. So from here, this tells us that k max then is going to be equal to what? Lambda minus L minus 1. This is then the maximum k value at which we can sum this thing to. So our maximum k value then is going to be dependent on this L value. So for any given n, or sorry, any given L, we have a k max, which basically means that our sum then is going to go from 0, k equals to 0, up to that k max value. And then this is going to give us a non-infinite divergent term. Let's give us non-divergent. So as I mentioned last time, basically this type of scenario is what's called the Laguerre polynomial, which basically means that instead of doing an infinite sum, we're summing only up to some maximum amount of value, which means that, pardon me, that we are truncating our sum at a particular maximum point, which makes it what's called the Laguerre polynomial instead.
Just a quick question, Professor.
Sure.
Since you're terminating the sum, does it then become an approximation, or is it still exact?
It's still exact. It's still exact. The only problem there is, I don't want to say that. What do you mean by an approximation in this case?
I'm just thinking like a Taylor series. You know, you go out to, if you only go out to a finite number of turns, you get an
Oh, I see. Yeah. So in that case, no. So it's not like a Taylor series where if you truncate at like 5 terms, then you can get better precision if you go further. No, this one is forced on the fact of us that we don't want it to diverge, so we're going to sum to that maximum point.
Okay.
So again, typical Laguerre polynomials, they do things like that as well. So you sum only to some maximum level. So no, so it doesn't make it non-precise, but it does make it, I don't want to say this, but this is true for any type of special function. It just makes it a special function.
Okay.
I guess this is the best way to say it. Right, because your Bessel functions and all those things are defined as sums over particular things. So they're not, it's not a closed form. It's just defined as a sum instead, if that kind of makes sense. Good. So we can solve this actually for lambda, and then it says lambda then is equal to k max plus L plus 1. Now this is where the quantization of the hydrogen atom occurs, because here k must be an integer. Right? This guy has to be within the integers. L must also be an integer. This guy is also within the integers. 1 is also an integer, so basically what that forces upon us then is that lambda here is also an integer. So basically this is where the quantization of the hydrogen atom comes from, is because these guys are all integers, and we're forced to the fact that we can only sum this thing up until where the recursion relation becomes 0. So again, up to some sort of k max value, which means that since everything here is an integer, that means this guy has to be an integer as well. So this is where the quantization of the hydrogen atom occurs. So this gives us the quantization of the hydrogen atom. And like I said, so what this means then is that U of rho depends on F of rho, and then F of rho, since we're only summing to a finite level, this guy is called the Laguerre polynomial. Since only summing to a max value. And that max value, again, is dependent on L. So this depends on L. So good. So lambda, remember by its definition, so let's go back to lambda. So lambda is actually in terms of the energy, so we can actually rewrite the energy in terms of lambda. So this means then that the energy is also quantized because lambda is quantized because it can only then come as an integer. Right? So remember, lambda here is equal to z e squared divided by h bar square root of mu divided by 2 times the energy, at least the absolute value of the energy. So from here, what we usually do is we're going to redefine lambda as n, where n is what's known as the principal quantum number. And it's called the principal quantum number because, as we can see from here, it tells us about the energy. So the principal quantum number tells us about the energy of our hydrogen atom. So if we solve this, what we should find then is that the energy is equal to negative. Again, it's negative because we're restricting it to be negative for a bound state. Mu times z squared times the charge to the 4th divided by 2 times h bar squared times n squared. So this then is the energy of the hydrogen atom, or hydrogen-like atom, I should say, because here we're letting Z here go to anything, not just one. Where here n, again, is equal to an integer, a positive integer, except 0. So this just means n is equal to 1, 2, 3, blah, blah, blah. So it's a positive integer except 0. Have you guys seen this notation before?
Just not the 0 under the bar 0.
Just not the
Yes,
bar
sir.
0 before? Gotcha.
Yeah.
Yeah, anytime you write it like this, it just means it's this excluding this.
Okay.
Yeah. So it just means exclude. Clayton, did you work last night?
No.
No? Nice. Good for you.
They let me have days off sometimes.
That's true. So good. So from here, we can usually define a new quantity called alpha, which is equal to E squared divided by H bar C, which is what's known as the fine structure constant. So in this case, if we use alpha into here, we can actually then rewrite the energy E as then being minus mu times C squared times Z squared E to the 4th divided by 2n squared. Oh, good. So this is then our energy of the hydrogen atom. So good. So again, this is where the quantization comes from. Again, quantization comes from the fact that we can only sum this to a maximum K value. That maximum K value then forces this term here, which is related to the energy, to be an integer, which means it has to be quantized. So in this case, defining our principal quantum number, which is also an integer because the energy is an integer, forces this whole entire thing to be quantized. So this is actually where the quantization of the hydrogen atom occurs from. So good. So let's look at our hydrogen atom wave function, or our hydrogenic wave function. So good. So we now know that's what? The inner product between R and N, L, and M. So before we wrote this as E, L, and M, but now I'm just going to replace it with N because N tells us about E anyway. So that's the, again, principal quantum number. We wrote down before was equal to R, which depended on R, and then the YLMs, right? Theta and phi. So in general, what's going to be true here is that R is also going to depend on N and L. So we've already seen it depend on N, but N depends on L anyway. So we're just going to write it this way. So, or we can write this in terms of U. So it's going to be U and L of R divided by R times our YLMs. So this is our total wave function. So it's the radial portion, which we just solved for, times then the spherical harmonics. So to get kind of a better idea of how this thing actually works, let's consider a couple cases and kind of build in our wave functions and see what these things should actually look like. So for example, let's start off with n is equal to 1. So if n is equal to 1, then we know this is then equal to k plus l plus 1, right? Which basically means that what? Since this guy cancels with this guy, that means that k plus l must then be equal to 0. And the only way for this thing to be 0, since we can't have negative L values, we can't have negative K values either, the only way that this thing is going to be equal to 0 is if both K and L are equal to 0. Good. So basically what that tells us then is that our wave function which is going to go with 1, 0, 0. And this is 0, 0 because if L is equal to 0, M is also equal to 0. So this also forces M is equal to 0. Because remember, M, oops, is going to be somewhere between negative L and L. But if L is equal to 0, then this is only forced to be 0. And this guy's going to be equal to R, 1, 0, R, Y, 0, 0. So this is our wave function. So good. Whoa, what happened here? Go away. So good. So basically what this means then is we're only summing to k is equal to 0. So we're summing from 0 to 0. So that's pretty nice, right? So good. So from our recursion relation, what this says then is that what? Ck plus 1 is then equal to Ck times a whole bunch of stuff, right? So let's go back to our recursion relation. Let's see if we can get this right. So this is then Ck times K plus L plus 1 minus N, all then divided by K plus 1 times K plus 2L plus 2. Okay. So for us, that means C1 here is going to be equal to C0. We know K is equal to 0, so we start off at 0, times then 0 plus 0 plus 1 minus 1, all divided by stuff. Oops, that should be a 1 and an N. Which is equal to 0. So basically, what this means then is that we only have one non-zero coefficient, which means f of rho then is simply going to be equal to C0 times rho to the 0, which is simply equal to C0. Which means then that U of rho then is going to be equal to rho to the L plus 1, but L is going to be 0, so this is then 1, times e to the minus rho divided by 2 times C0. Guys doing okay? Which means R, 1, 0, then is going to be equal to rho, e to the minus rho divided by 2, C0 divided by R. Now, if I use the definition of rho and plug all that in, what we finally get then is, I'm going to skip some steps, but we get R10 then is equal to 2 times Z divided by A0, I'll define A0 here in a second, e to the minus Z times R divided by A0 times C0. So this is my R10 term, where A0 here is equal to H bar divided by mu C alpha. This guy is what's known as the Bohr radius. So this is the definition of the Bohr radius.
Quick question, Professor.
Sure.
Is c the speed of light in this case?
No, this is C0. That's just that coefficient. Oh, you mean this C?
Yeah, let's see.
Yeah, that C is the speed of light. Yeah.
Okay.
Yeah. Sorry, I said C and I was looking at this one. Nice. Good. So basically, to get C0 here, now all we have to do then is normalize our wave function, right? So as we know is that what? 1 then must be equal to the integral from 0 to infinity then of what? drr squared modulus of r and L modulus squared. Right? So this must be true. And we talked about this last time. The reason for that is because the spherical harmonics normalize themselves, so we can normalize the radial portion individually. So good. So let's plug in. So this becomes the integral from 0 to infinity of drr squared times this stuff. So this is then going to be 2z divided by a0, e to the minus z, dr divided by a0. Actually, all this stuff is squared. So I actually need a 2 here, times the modulus of c0 squared. So most of the stuff is constant, so I can pull that out. So this is going to be equal to 2z divided by a0 squared times modulus of c0 squared times the integral from 0 to infinity, then drr squared e to the minus 2zr divided by a0. Take an integral of an exponential, I just get what? The exponential back divided by the derivative of the exponent. So this is going to be what, 2z divided by a0 squared modulus of c0 squared. And then I get a what? Negative a0 divided by 2z. All times e to the minus 2zr divided by a0, evaluated from 0 to infinity.
Question, Professor. Since
What's
you've got the r squared there, don't you have to do integration by parts?
Oh yeah, you're right. I got all ahead of myself. Good. Yeah, you're right. I forgot about that r. Good.
Well, maybe you can do a substitution. Would you be able to do a substitution with that one?
You do a substitution. Well, we could do derivatives of this, right? So we could do. So one thing we could do is define all this other stuff here by. So we could say something like b is equal to. So let's do 2z divided by a0. So let's do something.
R though, wouldn't you?
So a0 squared c0 integral 0 to infinity drr squared e to the minus what, br, right? So now if we took what, 2 derivatives in respect to b, then that would then bring down an r squared, right? Because if I did db squared of e to the minus br, then that's going to be equal to what? R squared e to the minus br, right?
Don't forget your b.
What's that?
Don't forget your b squared there.
My b squared?
Oh, because on the right-hand side, if you take the 2 derivatives, wouldn't you end up with a b squared there in front of that?
Oh, no, I'm taking a derivative with respect to b, not with respect to r.
Oh, duh. Sorry.
You're fine. Good. So we did that. So let's do a cheat way. There we go. So c0 squared. So basically, we can pull out that 2 derivatives of b, and then we can now look at the integral of dr e to the minus br from 0 to infinity. So that was the thing I originally did. Doing okay?
Yeah. Yeah.
Much better now. Good. Good. So let's go ahead and do that. Modulus c0 squared. Again, if I integrate this, I'm just going to get, since I'm integrating with respect to r, I'm going to get a 1 over b squared, right? Or no, 1 over negative b. So this is going to become equal to db, the 2 derivatives, times negative 1 over b e to the minus br, evaluated from 0 to infinity, right? For r. Now, at infinity, all that's going to happen is this thing's going to go to 0. If I do to 0, am I integrating from 0 to infinity? Let's see here. Yeah, integrate from 0 to infinity. Right, so if I do then 0, this then simply becomes 1, right? So this whole entire term is going to become just plus 1 over b. And I'm going to take 2 derivatives of that, which is then going to give me a what? A b cubed, right, on the bottom? That sound about right? Take 1 derivative, I get a b squared on the bottom, and then take another one, I get a b cubed. Yeah. So this thing is going to go as negative 2z a0 squared modulus c0 squared times then, or divided by b cubed. One derivative, get a negative. Oh no, positive. So I get one derivative from that, gives me a negative. Second one gives me a positive. Okay, good. If I knew how to do derivatives, my life would be better. Okay. Guys doing okay?
I think so.
Good. So now if I use this definition in here, cube that, and then cancel terms, this thing is then going to become simply A0 modulus Z0 squared divided by Z. Now, since all this is equal to 1, now we just solve this for C0. So finally I get C0 then is equal to the square root of Z divided by A. Put all this together, we finally get R10 then is equal to 2 times Z divided by A0 raised to the 3/2 power times e to the minus ZR divided by A0, which finally means that our wave function R of 1, 0, 0 is going to be equal to this times y0, 0, but y0, 0 is simply 1 over the square root of 4 pi. So times 2 Z divided by A0, 3/2 e to the minus Z divided by times R divided by A0, where y0, 0 is equal to 1 over the square root of 4 pi. It's just a constant. Let's do another one. Let's make sure we know what we're doing here. So next one we're going to look at is the first excited state. So let's do n is equal to 2. So if n is equal to 2, we then have n is equal to, again, k max plus L plus 1. Since this guy's equal to 2, that gives us 1 then is equal to K max plus L. Mm-hmm. Now, as we also talked about last time, L it could be equal to anywhere from 0 to n minus 1. Okay. So basically from here, we have two different choices for L. Dots in there. So that means that we have two choices. So if we have L is equal to 0, what that means then is that K max must be equal to 1. And if L is equal to 1, that means K max then is equal to 0. Okay. So these are our two different choices. So let's look at this case first. K max is equal to 1 when L is equal to 0. So we have L is equal to 0, K max is equal to 1. So in this case, we have C2 then is going to be equal to, using a recursion relation, C1 times 1 plus 1 minus 2 divided by 6, which is equal to 0, which means C2 is going to be equal to 0. C1 then is going to be related to C0 by C0, negative 1 divided by 2, which is then equal to minus C0 divided by 2. So for here, F of rho then is going to be equal to C0 times rho to the 0 plus C1 times rho to the first power. So this is going to be equal to C0 minus C0 divided by 2 times rho. So this is our F. Is it okay? So from here we can find the wave function. So then we have R2, 0, 0 equal to R2, 0 times Y0, 0. Where then R2, 0 then is going to be equal to, so again we're going to have a rho to the L, but L is 0, so that's 1, times e to the minus rho divided by 2 times F, but F now is C0 minus C0 divided by 2 times rho. And all this is divided by R. Okay. Now plug in what everything is. So this thing is going to become equal to, so it's going to become z, c0 divided by a0, e to the minus z r divided by 2a0 times 1 minus zr divided by a0. So this is our r20. So again, here we would then have to normalize this thing to then find what C0 is. So again, we want to take 1 is then equal to the integral from 0 to infinity, dr r squared of the modulus of r20 squared. Here I'll skip the math, but basically what we find in this case then is this becomes z C0 divided by a0 squared times 2a0 cubed divided by z cubed, okay? Which means then at C0 then is equal to the square root of z divided by 2a0. So putting this in our wave function then, 2, 0, 0 is going to become 1 over the square root of 4 pi again, since again y0, 0 is that, times then z divided by a0 raised to the 3/2 power, e to the minus zr divided by 2a0 times 1 minus zr divided by 2a0. So that's when L is equal to 0. The next one we can have is when L is equal to 1. L is equal to 1. That means M then is equal to -1, 0, or 1.
Real quick, Professor, could you back up just from a slide real quick?
No problem. 1 second here. There we go. Previous. There we go.
Okay, that was all I needed.
So good. So in this case, we're going to have actually 3 different YLMs right from here. So we're going to have YL1, or sorry, Y11, because that was 1. So one possible is this one. We're also going to have Y10 and then Y1 -1. Right? So these are our 3 different possible YLMs, which means we're going to have 3 different wave functions for this particular excited states when L is equal to 1. So the wave function we're looking for here then is going to be R 2, 1. And now from here we have again the 3 different ones. So we're going to have either 1, 2, 1, 0, or then 2, 1, -1. That's going to be equal to R21, Y11, R21, Y10, and R21, 1, -1. So let's look for this guy. So again, from here, what we have then is that what K max is equal to 0, which means that C1 again is going to be equal to 0, which means we only have C0, which means that what? F of rho is simply going to be equal to C0, which means then that R to 1 is then going to be equal to rho. So here I have squared, because I have a 1 plus 1 times e to the minus rho divided by 2 times then simply C0, all divided by R. Okay, so just remember here, this one comes from the row L plus 1. So L in this case is 1, so that gives that guy a squared. Plugging the values for what rho and all that good stuff is. So this thing is the same thing as z squared C0 divided by A0 squared R, as this R is going to cancel with one of those, times e to the minus zr divided by 2a0. Again, here, if we normalize this, what we find is that C0 then is equal to 1 over 2 square root of 6 square root of z divided by a0. So that r to 1 is going to become 1 over the square root of 3 z divided by 2a0 raised to the 3/2 power times z times r divided by a0 e to the minus zr divided by 2a0. I think my jaw is starting to hurt because I'm talking too much. Okay. So good. So from here, we would just plug these back into here. So this term would be here, and then use what y1 is, y10, and y1 -1. So y11 is equal to negative the square root of 3 divided by 8 pi sine of theta e to the I phi. Rho 10, hello, is equal to the square root of 3 divided by 4 pi cosine of theta. And then y1, oh, I got those backwards. Sorry, this should be positive with a negative, and then this one is negative square root of 3 divided by 8 pi sine of theta e to the I phi. Sorry about that. I was looking in the wrong order. You guys doing okay? I'm talking to a couple of class. Oh, you're fine. Just quantum mechanics. Awesome. Nice. Good. So basically,
I missed the last one, Professor.
what's up?
I missed the last y function.
There you go.
Didn't quite have time to get that written down.
You're fine. You're fine. So yeah, those are all those guys. Yeah.
Okay.
So it turns out that we can actually write this as a special function using the Laguerre polynomials that we talked about. So basically, it turns out that f of rho is actually equal to L. I'll tell you what L is here in a second. This is what's called the associated Laguerre polynomial. This is equal to 2L plus 1 n minus L minus 1 rho, where this guy, L, I'm going to call that P, and then I'm going to call it Q minus P of X, is then defined as -1 raised to the pth power times then the pth derivative of then LQ of X, where LQ of X here is the Laguerre polynomial, which is then defined as e to the x times the qth derivative of e to the minus x times x to the qth power. So, yeah, so we can actually write this then as this polynomial, and then put this all into one nice compact wave function, which means our total wave function then, which depends on L, N, and M, is then going to be equal to the square root of 2z divided by n, a0 raised to the 3rd power, times n minus L minus 1 factorial divided by 2n times L plus n factorial cubed times e to the minus zr divided by na0 times 2zr divided by na0 to the nth power times that associated Laguerre polynomial to the 2l plus 1 n minus L minus 1, which is a function of 2zr divided by na0 times our spherical harmonics ylm theta phi. So this is the most general way of writing the hydrogenic wave function. That was a mouthful. Skip some of that stuff. The last thing we're going to talk about real quick, because we're almost out of time, is the degeneracy of this thing. So basically, as we talked about, what L can be anywhere from 0 up to n minus 1. And we know M can go anywhere from what? Minus L to L. Mm-hmm. So basically, this thing has a whole bunch of degeneracy. So what that means then is that for any given L value or N value, then that means this thing is what? From here, this thing has 2L plus 1 worth of degeneracy. Right? So basically, if I put that in, then this thing is, for my given N value, this thing is from L is equal to 0 to N minus 1 of my 2L plus 1, which actually is equal to N squared. So basically, all this means is that for any N value, so for any energy, my wave function then is N squared degenerate. So for example, the ground state, what that means then is non-degenerate. It actually is, we'll talk about that in a second, but this would imply then that it is non-degenerate. But then the first excited states then would be fourfold degenerate. And then the next state, right, would be the second, would then be ninefold degenerates, and etc. But it turns out there's actually another degeneracy because each one of the proton and the electron also has a spin associated with it. So both the proton and the electron are individually twofold degenerates, which means that there's an extra fourfold degeneracy on top of this. So the total degeneracy then of the hydrogen atom is actually equal to 4n squared, which means that the ground state of the hydrogen atom is actually fourfold degenerates, because for the n value, it is not degenerate, but because of the 4 different possible spin states, then it's fourfold degenerates. So in all, the degeneracy, without taking other quantum corrections into account, is then 4n squared degenerates. So for the hydrogen or hydrogenic atom, then this thing has a 4n squared degeneracy to it. Now, the kind of surprising thing about this is actually the energy is not degenerate. So this is actually what's known as an accidental degeneracy. I can't spell. Accidental. Degeneracy. So basically, what that means is, again, even though this thing is degenerate, but the energy, as you remember, is not a function of what? L and M. It is only a function of N itself. So it's only a function of this guy. So the lack of the degeneracy on the energy is actually, in respect to L and M, is actually kind of surprising. It's actually kind of weird. You would expect it to be degenerate, but it's actually not. Right? So this is why it's called the accidental degeneracy, because those things are not dependent, at least the energy is not dependent on L and M. So nice. We finished with 2 minutes left. Cool. We got all of our objectives done.
Just barely.
Just barely. About 1 minute, 45 seconds to spare. So, any questions at this stage?
So we're not meeting Tuesday then?
Well, Tuesday is during finals, right?
Oh, it is? Okay.
Yeah, tomorrow's actually the last day of class, and then finals starts, what, Monday?
Okay. So they changed. I haven't looked at the schedule in a while. I did not realize they changed it. Okay.
Yeah. Let's take a look here. At least that's what I understand.
Okay.
That was my understanding. So let's take a look. Academic.
You just having the 2-day strangeness going on.
Wait, what was that?
I said I'm just used to having the 2 days of class and then the break it down.
Oh yeah, because they changed everything because of, you know, all the other good stuff. So
Yeah.
right, which is why we lost a lot of things and gained some things and did some stuff. Yeah. So yeah, the final exams technically start Monday.
Okay.
Well, actually, technically Sunday. I don't know why they included Sunday on there, but yeah.
Okay.
Actually, no. Starts Saturday, according to this.
Oh, aren't they lovely?
So it's actually Saturday through Friday. So I guess they're including Saturday and Sunday as your guys' reading days. So,
How nice of them.
it is. It is. So yeah. So yeah. So is it? So I'll post the final. That'll be due Friday.
Okay.
And then you guys have that other homework I just posted. That'll be due Tuesday. So we just get one more homework in because I want you to do a little bit with all this new stuff before it's actually on the final.
Okay.
And I'll try to remember to actually post all the homework solutions because I think I only posted the first homework solution and that was it. So I'll have to make sure I go through and post all those. Yeah. That's about it. So because we're basically out of time, so we'll probably skip the talk. So let's have you guys write the paper.
Okay.
I'll just roll those points into other things instead. So yeah.
So when will the paper be due? When will we have to start working on
So
that?
we'll make the paper due on our formal day of for our final because we were supposed to. The paper would usually be due on that day with the talk, but like I said, we're kind of running out of time here. So when is our final exam? So final exam schedule. That's fine. So according to this, it should then be Tuesday.
Okay.
Now, if you need more time than that, just let me know. But
Okay.
like
I have not started on it yet.
so for now, tentatively, we'll put it at that Tuesday.
Okay. This is gonna be a fun week.
Finals always are. Alrighty. Okay, so I'll post that exam. I might post it a little bit earlier, just give you a little more time to work on it, but we'll see. I'll have to see how ready it is. Other than that, you guys doing okay?
Yeah, I mean, sort of.
There we go. That's the attitude. All right. So on that note, I got to go find some food. So I will talk to you guys later. Let me know if you have any questions on anything. You can always meet, do all that good stuff. So.
Okay. I'll see that, Professor.
All right. See you later.